Good morning, ladies and gentlemen of Precalculus. In these exercises here, starting with 13, we're introduced to this thing right here, which is ln. Do you know what ln is? You know what ln is? Anybody? Okay, ln means natural log. What it is, it comes from the French. It was be logarithme naturel. So that's how they got ln, because it originally came from. Does that sound right? Does that sound like French? Logarithme naturel?
Yeah.
It is French. Anyway, it means a natural logarithm. What that is, that's going to be log base e. That's what logarithm, natural logarithm is, log base e. And you know what e is? E is something called Euler's number.
Oh, it's
Justin, you know what it is, right, Justin? It was in chemistry. You use this for
something point something times something to the 10,000.
Well, no. What this is, it's approximately. That's an irrational number. It's going to be 2.718, and you can actually find that on your calculator. I will show you. Clear this out. It's this thing right here. So if you go to second, you have E, and you press enter, you get this. So that's where it is. That's where you find it on your calculator. And it has special properties that are very helpful in finance and in calculus. So that's about as much as I can tell you right there for compounding. And we're actually going to use this number in this section, in this chapter, to do compounding, continuous compounding. So that's something to look forward to. So anyway, what I'm going to do is rewrite this number 13 is log base e of e to the power of 3. And if we set that equal to x, what is this going to be equal to? Okay, it's going to be e to the power of x equals e to the third power. So e equals, or x equals, x is equal to 3. Okay? And you know where the ln key is on your calculator, by the way?
Yeah.
That's this one right here. See that? That's your natural logarithm calculator key. Speaking of, I know this is non-calculator section, but here, in case you need. All right, so what I want to do is, I think number 14 is eminently solvable by people in the class, especially Justin.
What?
Justin, I might pick your name here, who knows? We'll see. We have a small enough class that we will pick everybody at some point. Okay, and Chloe will be back next week. But right now, problem 14, that's going to be one of our favorite students here, which is Elizabeth. Elizabeth is all ready. She's always ready. All right, Elizabeth, what did you get for 14?
It's going to be x equals -4.
The way Elizabeth said that, it sounded like she was almost disappointed. Right? You wanted to have a harder one, didn't you, Elizabeth?
I did not want 15, that's for sure.
Oh, you didn't want 15, okay. But anyway, it's the same thing here, right? Because if you have log base 10 of e to the negative 4th power, and that you're trying to find out what that equals, well, that's going to be 10. That's going to be, I put 10 there. I meant to put e, right? Sorry about that. That's going to be e to the power of x equals e to the power of -4, and so that would be your answer. So, Elizabeth, you're telling me that 15 looks a little bit monstrous to you? Okay, fine. What I will do for this one is natural logarithm of 1 over e. Should I spin the wheel on this one, or should I do this one?
I think you should just do it.
Spin the wheel.
I think I should spin the wheel. I
Okay,
believe.
spin the wheel.
I'm
Yeah,
ready for it.
Spin the wheel.
You ready for anything?
Yeah, Robert's gonna get it.
Whoever it is, I'll work with whoever it is, or Robert will work with whoever it is.
Robert, I hope it's you.
You got this one too? Becky says you got it. All right, yeah, I'll spin the wheel then. All right. I'm gonna shuffle 2, 3 times. You don't know how to do this one?
No?
Okay, I'll work with you. Or others will work with you. You'll be good, you'll know how to do this. So, can you just talk about maybe what you might start doing on this?
Would it be -1? Because.
Okay, so Riley has a theory of x equals -1. Let's go ahead and do that. So were you just instinctive like that?
Yeah.
Okay, let's go ahead and work this out, because that actually might be right. So if we have log base e of 1 over e, and that's equal to x, we have e to the x equals 1 over e. And then according to the properties of negative exponents, that's e to the -1 power, right? So e to the x power equals e to the -1 power. So that's a correct answer. And you were just instinctive like that. Are you just like an instinctive logarithm genius? Is that what you are?
Yeah.
Okay, she is. I like that. No false humility. No false humility going today.
Oh, shoot, sorry.
All right, this one here, we're going to spin a wheel on this guy. Okay, I'll shuffle this once. Here we go. It'll be Robert or Karina. It's going to be Karina. Okay, Karina, what do you think? Zero. So she has, if she sets this equal to x, then we have log base e of 1 is equal to x, then e to the x is equal to 1, and we can rewrite this as the power of e is e to the x equals e to the 0, because e to the 0 power is 1, and x is equal to 0, so 0 is our answer here. Is that how you did it? You did it differently? How did you do it?
I'm not bothered with
How did you do it then?
it. If I do like log 10 equals
So like log 10,
9.
log base 10? What it is a lot of students will have their own way of thinking things that sometimes seems a bit instinctive, and it's a good way of looking at things. So if there are ways you can think of to do things, we want to hear from you, okay? Here we go. One of Okay, number 17. Okay, let's see what this one is. Let's see, one more shuffle, let's go here. Is it gonna be Becky? Looks like it is. All right, Becky. What do you think? What'd you say?
No, that one, 0.25
So 0.25,
or 1/4.
so 0.25 or 1/4. Let's go ahead and break this down. So we got log base 10 of the 4th root of e is equal to x. So you have 10 to the x is equal to, that's going to be, or e, now I still put that 10 there. That's a habit, it's a bad habit. Not a bad habit, it's just a habit. That's log base e, right? So e to the x equals 4th root, and that's going to be e to the 1/4 power. So x is equal to 1/4, right? Or 0.25, so, right? Is that how you did it? Did you use a calculator?
Yeah, I mean, I understand that one because it was like,
Okay,
I was like putting in the calculator, that's how I did put in the calculator though.
okay.
So, I was like, how do you do this one?
Oh, okay, I see what you're saying. That's how you do it. It's not bad. Let me call up somebody else here. We know we have fewer victims on the wheel right now. We're going to do some more exercise. There we go. And okay. We know who it's going to be. We know within range who it's going to be. I'm not even going to shuffle when we get to the. All right. Robert, what do you think?
I did this one on the calculator and I got -3.5. But he showed us how it.
Okay, can somebody talk about this, right? We're supposed to be doing these without a calculator. So this is log base e of 1 over square root of e to the 7th. Yes,
It makes it to the -1/2.
okay. So you would say this is going to be log base e of e to the 7th to the -1/2. Is that what you're saying, Nicole?
Yeah.
Okay. And that's equal to, it's supposed to be equal to x, right? So what next?
And then you just put the 7.
So I'm just going to come over here. So we have is e to the x equals e to the 7th power to the -1/2. And so we get e to the x equals e to the -7/2. So x equals -7/2. All right. That wasn't that hard, right? Okay, Robert. Oh, this is a different one. That's a harder one. I mean, it's unfamiliar, but I'll do that. So I'll go ahead and do number 19. Well, I want you to do another one, Robert, without your calculator.
Right.
Maybe number 20. Okay, here we have a situation where this logarithm is in the place of an exponent. You see that? So 7 to the power of log base 7 of 3. If you were just being your instinctive self on this, what would you think an answer might be to this?
Would you,
I would say
seven.
1, 4.
would you find the exponent and then?
Yeah, so let's go look at this. Now, I'm going to go ahead, we're going to change, this is in exponential form. We want to go ahead and turn this into logarithmic form. Okay, so we want to change this to a logarithm form. It's going to be, this is our base of a logarithm, right? So log base 7 of x, do you see what I did? That's the base of x is equal to log base 7 of 3. So we've converted this exponential equation back into a logarithmic equation. So what is our answer here? 3. And so x is equal to 3, so 3 is our answer. Now, what's happening is this 7 to the power of log base 7, this is actually just ends up equaling 1. So it's like they cancel each other out. Okay, so 7 to the power of log base 7, they cancel each other out. And so does that prepare you, Robert, to help us out with number 20?
Yeah.
Okay, Robert sounds like he has some confidence. So what do you have for this one, Robert?
I'm gonna give you that first, which is x equals 8.
So 8, right? So
Yeah,
8.
now the work is, the bottom I put log base 5.
So you have 5, you have log base 5 of x
So that's equals.
equals log base 5 of 8. So
And
x is equal to 8. Okay, very good. All right. About that. Sorry. Throwing the paper off the desk. That wasn't my intention. I'm not trying to be disruptive. Okay, next. 21. Okay, we have, okay, it's going to be Justin or it's going to be Nicole. That's just what it's going to have to be here. And then so Justin's now, Nicole will be next. Okay, Justin, what did you get for this one?
I don't know.
not just
Let me see what 22 is. 22 is very similar. Okay, Justin, here. I will show you, okay? So we have 10 to the power of, what do we get?
So would the little number be 10? Because there's nothing there.
Yeah, right here, like that, you mean? Yeah.
That's all I got.
That's as far as you got?
Yeah.
Okay. So we already have, if we set this equal to x,
Oh, okay.
then, and we change this to a logarithmic function, we have log base 10, because this power becomes the base of x, is equal to log base 10 of 0.5. And so what is our answer here? X is equal to 0.5 or 0.5. Okay, so that's all there is to it. So Justin, what I want you to do for us is do 22 for us.
Is that right? Oh, you said number 24. Oh, I wrote that one wrong.
Well, he did this one, he did that one, right?
So, yeah.
All right, Justin did, I'll tell you what, Justin's gonna help us out with number 23, because he did the wrong one here. Nicole, did you do 22?
Yes.
All right, Nicole, what did you get for 22?
X equals 1.4.
X equals 1.4. And they just collapse each other, right? So log base 10 of x is equal to log base 10 of 1.4. So x is 1.4. All right, thank you, Nicole. And that gets us to Justin. Justin, what'd you get for this one? Number 23.
So it's log base E
So log base e, he says,
6
6.
equals log base E.
So log base e of 6 equals x, or, well, it's going to be e, right?
Oh, yeah.
Yeah, let me rewrite this. I need to rewrite this thing. So e to the power of log base e of 6 is equal to x. Is that what you wanted?
Yeah.
Okay. And so now we take log base e of x is equal to log base e of 6. Is that how you did that?
Yeah.
So x is equal to 6. Okay?
All I did was x with e to the power of x equals e to the power of 6. I didn't do the.
Oh, okay. Yeah.
Because I knew it canceled already.
Yeah, so you get a sense of what cancels out. This can be helpful. Yeah, that's the way to look at it. And this one here, I'm just going to, this one right here, our answer is going to be 1/5, right?
Yes.
For the same thing. So that gets us through this set of exercises. So what I want you to do is, I'm going to pick that up in a minute. But we're going to watch a video right now about, it's called Logarithms in the Real World. It's about 5 minutes long, and then I'll come and pick up your exercises while you do that. Okay? So here it is, Logarithms in the Real World. Logarithms in the real world. Over the past 30 years, the active direct use of logarithms in math has gone down due to the availability and use of calculators, the availability and use of computers. Long directories of tables and reference books were devoted to providing logarithms to make multiplication and division a lot easier. Logarithms were used in slide rules, the computation tool that had enough horsepower to get men to the moon. The great value of logarithms today is that they are used to make a sort of shorthand or code to make extremely large or extremely small numbers manageable and understandable. Logarithms are especially evident in science and in measurement. Our sensitivity to light is highly logarithmic in how we perceive stimulus or input from widely varying sources of light. The amount of light from direct sunlight, about 100,000 lux, is 1 billion times brighter than the light from the brightest star in the night sky at 10 to the negative 5 power lux. Between the eye, with the iris to adjust to the level of light, and the neural signal transmission to the brain, human vision is able to adjust to span wide extremes in light input amounts. The intensity of earthquakes is measured by a number on the Richter scale, and the Richter scale is scaled to a base 10 logarithm. For instance, a 5.0 earthquake has 10 times the shaking amplitude of a 4.0 earthquake. Logarithmic scaling also gives us the measure of acidity. This is the pH scale. The pH of a solution is determined by a logarithmic function relating the hydrogen or H+ ion concentration in the liquid. Logarithms are used to describe sound intensity in decibels. The smallest sound a human can hear is defined as the threshold of hearing, or TOH. That volume is defined as 0 decibels. Every sound's intensity can be classified in decibels according to a base 10 logarithmic scale. Every multiple of 10 from the TOH translates to an increase of 10 on the decibel scale. For instance, a vacuum cleaner sound at 80 decibels is 10 times as intense as busy street traffic sound at 70 decibels. Here is a list of sound intensities. A normal conversation. Go ahead. So this is just sort of not. I mean, there's some subjectivity in this about what it is, but these are generally about what they are. And this threshold of pain, 120 decibels or 130 decibels. Sometimes you see it as 100. That's a big one. What else? A whisper, a very quiet whisper, is 20 decibels. And they all relate to actual wattage, power. A room at 60 decibels has 10,000 times the energy intensity as a whisper at 20 decibels. The light intensity of stars, planets, and comets is classified by magnitude. In 1856, a system for rating intensity was devised where a 0 magnitude light source is 100 times as intense as a 5 magnitude source. So every increase in magnitude is a multiple of the fifth root of 100. And a fifth root of 100 is approximately 2.51. So every increase of 1 in magnitude is really about a 2.51 factor of increase in brightness. Logarithmic functions are used to calculate ages by radioactive dating. An order of magnitude is an exponential change of plus or minus 1 in the value of a quantity or unit. The term is generally used in conjunction with power of 10 scientific notation. Based on that power of 10 scientific notation, anything that is 10 times as much of something would be 1 order of magnitude greater. For instance, $1,000 would be 1 order of magnitude greater than $100. Log base 10, or log subscript 10, is sometimes called the common log. And why is that? As humans, we have 10 counting digits on our hands. That's one of the most popular explanations for why we use a base 10 number system. Maybe aliens in different galaxies have a different common log than base 10. Maybe this guy and his alien species uses a base 8 as a common logarithm. On our graphing calculator, this TI-84 Plus Silver Edition, whose keypad is pictured here, there are 2 keys that represent logarithms, the common log or log key and the ln key below it. ln stands for natural log and has the irrational number e as a base and has properties covered in precalculus and in calculus. Find the common base 10 logarithm of a number by pressing the log key, then the number you want to evaluate, then press enter. What is being calculated here is the answer to the question, what is the power 10, or the base? What does that base of 10 need to be raised to in power to equal 10,000? And so a logarithm is a form of an exponent. We see that 10 raised to the power of 4 is 10,000. This has been Logarithms in the Real World. Thanks for viewing. So,
Now streaming on Disney Plus. Let Niche.
that's that one. Okay, we're gonna get started on another exercise. Yeah, you can go ahead. Where is that thing? I have it out here. Here it is. Yeah, that's fine. Go ahead. Okay, so this exercise set here is really. Oh, okay. All right. This exercise set right here is very similar to what we just got done doing. So it's really a refresher. I guess it's supposed to be the next day after it. But again, if we did this equals x, then if we take 10 to the power of x, that's going to be equal to 10 to the power of 2, so x equals 2 would be our answer. Does that make sense? And then you should be able to go through pretty quickly and do 1 through 4, right? Are you just zipping through 1 through 4? You've already done them, Karina? Yeah. Okay. This one would be 3. This one would be -2. This one here would be -3. So it's just what we did earlier. So, and then we get to 5 through 10, we're simplifying expressions. And so we're going ahead and working on our laws of exponents. And basically what you're doing is this is going to be equal to, using the quotient property, x to the power of 5 minus 2 times y to the power of -2 minus -4. And 5 minus 2 is 3. So we get x to the third power, and -2 minus -4 is 2. So this would be our answer for number 5. Does that make sense, Riley?
You're going to have fast, so
Yeah, so it's the quotient property of logarithms, which is if actually of exponents. I said logarithm, I didn't say exponent. If we have x to the power of a divided by x to the power of b, that's going to be x to the power of a minus b. And so that's how this was determined. Okay? So again, it's the properties of logarithms that we have mentioned a couple times here in class, right? So, no, I guess I can choose people for number 6, right? Open number 6. Here we go. So we have fresh wheel here, which I shuffled a couple times. Oh, Elizabeth, you're just really a glutton for punishment, Elizabeth. All right, Elizabeth, what'd you get for this one?
I got u to the power of -1 times b to the power of 5.
Okay, really good. Okay, that's perfect so far. But what you try to do, if you can, you try to get rid of those negative exponents. So you can, how can you rewrite this and make this -1 positive?
1 over u to the first, right?
Yeah, so it's going to be v to the 5th over u to the first power, which we'll just put as u like this, okay? Good job, Elizabeth.
How is it? Can you work that out?
Sure, yeah. I'll show it to you. Yeah, I'll show it to you here. Okay. What it is, this is going to be equal to u to the -3 minus -2
Isn't that
times
five?
v to the power of 7 minus 2.
Wait, why is it minus 2?
It's -4.
That's
Wouldn't that be 5?
No, it would be -1.
be -1, yeah. So that's going to be equal to u to the -1, because -3 minus -2, that's like -3 plus 2. And then v to the 7 minus 2, that's v to the 5th. And this is as far as Elizabeth got, and then we just fixed it to that, okay? Any questions about that?
Can you not erase it yet?
Okay. So this will be our most simplified answer for this one. Okay, next, I'll choose somebody for this one too. Okay, Robert, looks like it's you, Robert. Robert, the lucky one. Okay, Robert, what do we get for this one?
No idea, would you?
It'll be power of power. So distribute this 1/2 to these powers here.
So, 1/2.
Equals x to the, what's 1/2 of 6
3. Third power.
times y, what's 1/2 of -2? -1. And that's going to be equal to divided by y. Okay, does that make sense?
Yeah.
Okay, let's go. I want to finish this up here today because we should have this finished. It'll get us to a good stopping point. Okay, Robert, what do
Okay,
you,
so x, -6 power.
x to the -6 power,
And then y to the 8th power.
3, that's 36.
Oh.
Y to the 9th, how's that?
Oh, yeah.
So that's going to be equal
y to 9 over
x to the 6th.
x.
Okay, real good. Let's get to,
What was the answer you were 5?
yeah. Well,
X to the 3rd times y to the 2nd.
Over y to the second?
No, it's just times y.
Oh, just one.
okay, this one here is just more complexity here because we are really short on time. We have to wrap it up for this. So we're just gonna kind of finish these off tomorrow at the beginning of class and go on to the next thing, okay? All right, thank you.